So like here, goes, bam. Right here, it's the derivative is 0. And that's where this equation comes from, for the critical nucleus size, which is equal to minus 2 gamma T sub m over delta H sub f over delta T. Tm is the melting temperature. Delta T is the degree of supercooling. So the reason that in that video it was called supercooled water, do you know what the temperature is in the fridge? You have any idea? You don't know? It has to be below 0 centigrade, because ice forms there, right? In the freezer, everything's frozen. If it's not, something's wrong with the fridge, correct? I think it's around maybe minus 5 degrees centigrade. This is why the maker of that video had a problem, because he supercooled this water below 0 degrees. And he mentioned in the video that the water had to be pure, so he picked up Fiji water for whatever reason. If the water has impurities, those impurities act as solidification sites. A recent study, just recently that came out, determined that kidney stones have bacteria inside and biofilms. So the whole theory about forming kidney stones may be wrong. There's new research that came out. So you can apply this to kidney stone formation. It has to be a nucleus. Sometimes the surface of the bottle acts as the nucleation site. And for solidification of metals, for example, for the same exact reason, it's colder on the surface than on the inside of the ingot. Typically, it's very small. It's about 10 nanometers. Any questions about this? This is quite an important concept in material science of nucleation and growth. Do you understand why? Okay, so the surface energy tries to collapse it. So if you were below, it's going to redissolve. If we're above, then it's going to continue to grow. But it is the internal energy that drives the growth, where the surface energy is acting against the growth. And you can see this internal surface energy goes as a size squared, and the internal energy goes as a size cubed. Okay. As you remember in that video, things didn't happen instantaneously. So we are concerned about how fast this is happening. And so far, we talked about thermodynamic equilibrium. Now we're going to talk about kinetics, how fast the reaction goes. And this same concept applies to chemical reactions, to physical reactions, and we measure it as a degree of transformation. So as you saw in the video, the ice front propagated through the water. So from the video, you could measure how fast this transformation is happening in time. In other systems, how can we measure it? We can use X-ray diffraction. In fact, I'm working with Oscar here to do just that, to analyze the XRD data, to look at the titanium nitride barrier layer for the interconnects. The other one is electrical conductivity. This can be done on a simple one specimen. X-ray diffraction, you have many specimens, so you have to stop the reaction, take the sample out, take X-ray. Or the other ways to measure propagation of the sound waves, because the sound is going to travel differently in water than it is in ice. And the way sound travels through a solid in solid state physics, they call it phonons. That's the physics term. And those are lattice vibrations. Those atoms vibrate, and that's how they transmit the sound. The reason you hear me is because I'm vibrating the air, and the sound wave through this fabulous device with a microphone, through the speakers. But the same thing, the sound travels in the solid as well. And we can measure that. Okay, this is what it looks like, the curve. Fraction of transformed versus log of time. And typically, we have two, well, not typically, we have the nucleation side, where what was the size of that nucleus, the minimum size from that equation? Do you remember? About 10 nanometers. 10 nanometers is 1/100th of a micron. It's very small. So we start here in the growth part, and then the curve is nonlinear. So we start here, and then here's the transformation is complete. In the middle, we measure t.5. So at t.5, half of the phase is transformed. And it is described by the Avrami equation, which is 1 minus the exponent of minus kt to the nth power. And by convention, the rate of the reaction is the slope, which is going to be 1 divided by t.5. Okay? And as a result, we can make TTT diagrams. So the same concept can be applied for heat treatment, like recrystallization. If we're going to do this at 43 degrees, here's the curve, and here's the time. You can see the time is increasing, and it takes less time to do this transformation. This is the case of copper recrystallization. And you can see that the rate is increasing with increasing temperature. And because the way it works, you can really never reach equilibrium because the stuff becomes very slow because of low concentration gradient in the end, which is controlled by what diffusion law? There are two diffusion laws. The first Fick's law and the second Fick's law. We already discussed it. The first Fick's law, when you maintain, you keep putting stuff in. If you have like a compressor that blows through the membrane and you maintain the pressure, that is steady state. The second one was non-steady state. So to give you an example, this titanium nitride that we're working on right now, there's a process called RTA, rapid thermal anneal. 5 minutes. Then we have another set of samples that were annealed for 30 degrees, for 30 minutes, I'm sorry. And based on this approach, something that was annealed at 800 degrees C for 5 minutes is equivalent to the same thing being annealed at 600 degrees for half an hour. Right? So we want to know how fast things are happening. We're going to go back to this phase diagram, which is for steel, iron, carbon. And I spent the whole semester when I was an undergrad studying this. But there's this eutectoid reaction that you see here, 27 degrees centigrade. And the reaction is that we have 0.76 weight percent carbon, less than 1% carbon, which is decomposed to alpha phase, which has even less carbon, 0.022 weight percent. and 6.7% cementite, iron 3C. So to maintain this reaction, we need to undercool it, meaning that the temperature has to be much less than 727 degrees C. And remember, we started the class by, I gave you an example. You take 3 samples from the same larger piece. You put it in the furnace, and then you put one in ice water, you put another one in oil, and you put the third one to be let and cooled in air. And the hardness as a result is going to be a factor of 3. I'm going to explain to you why and how. So we have the eutectoic transformation of austenite to pearlite, and this is how it goes. So here we have ferrite alpha and the cementite in between. And this transformation happens by the diffusion of the atoms carbon from the gamma phase into the alpha phase. So here's the carbon diffusion. You look at this. Please look at this scale. This is logarithmic scale. 1 second, 10 seconds, 100 seconds. At 675 degrees centigrade, we compare that to this temperature, 727. And you can see where this temperature, it's going to take 100 seconds for half of the phase to be transformed. At 650, we drop down the temperature by 25 degrees. You see here? It's going to take, 20 seconds. And then we drop it down further to 600 degrees C. So the difference in temperature between 727 and 600 is going to be 127 degrees centigrade. It's going to take, 3 seconds. So this is the difference. And as a result, we can find coarse pearlite, which is formed at high temperatures, and this is going to be relatively soft. Or we're going to have fine pearlite, which is going to form at lower temperatures, and that's going to be relatively hard. This is the difference between ice cold water and cooled in air. Does that make any sense? Okay. What can you do to triple your starting salary when you get your degree? Every day in our life, we're looking for small, tiny increments. The gas went up. I was driving. It's over $3. Well, you know the reason why. But percentage-wise, that's like 10% in one day or a couple of days, like over the weekend or whatever. What are you going to think if the gas is $10 tomorrow? What are you going to say? Are you going to be outraged? Do you think it's possible? So you have a natural system where a property can be tripled, and you're not doing anything special. You're not adding more gold or nanoparticles or anything like that. You just take the sample, you cut it in 3 pieces, you put it in the furnace, and then you just cool it at a different rate. I don't know. I find it to be magic. But now I'm explaining to you how it's physically happening. So, we get this data. And I showed you that you can get it from XRD, you can get it from sound waves. From this data, we are constructing nose diagrams. The reason they're called nose is because this looks like a nose. You see? And there are 3 curves typically. There's a green curve, which is 0%. You have the red curve, that's 100%, and you have a dashed line here, that's 50%. This is temperature versus time. And you need to know how to read them. But that's where they're coming from. They're getting from the percentage transform. So from the integrated intensity, Oscar, that we need to figure out how to do it right. This guy sent us the data and his interpretation, and we need to get the intensities right, the integrated intensities right, so we can find the percent transformed, and from the percent transformed we can make this nose diagrams based on the real data. So far it's been, I mean, I'm trying to explain it to this guy, but it's been like a month and not much is happening. So Oscar wrote the code in MATLAB to fit the data, and because the data is noisy and sometimes there are two reflections in one. So this is applied to metals. We're applying it to ceramics and semiconductor manufacturing. So I think the impact is going to be huge once the work is complete. Do you have any questions about this? Whenever you see the data is always plural, by the way. Data are expensive to get. Yes? Yeah. No, I always test back, so I'm not ahead. If I pull up the syllabus, I'm behind. Yes, ma'am. It's not going to be on the exam. I worry about, oh shoot, I don't even have this. There's austenite to pearlite isothermal transformation. What does isothermal mean to you? Iso, same temperature, very good. So you can see here, okay, isothermal at 600, whatever, 50 degrees. Right here we have gamma phase, austenite. You see? And there's zero pearlite. Over here, at this temperature, you can see that there's pearlite that forms around the grain boundaries. And then if you hold it at this temperature this long, then it all turns to pearlite. You see that? Do you understand? So if we go from here to here to here. And the properties are totally changed. They're totally different. Okay, you can also take a non-eutectoid composition. So this is eutectoid composition right here. Remember hypo-eutectoid and hyper-eutectoid? Over here we're going to form more cementite, iron 3C. And another really cool structure is called bainite. If we go below the nose, so this is the nose curve, if somehow we can provide, for maybe a small part, a higher degree of supercooling that you see over here, we can form bainite, which are streaks of this iron 3C that makes the structure super, super hard. Another one is spheroidite. This is when the iron 3C particles are actually seen right here. Okay, so this is alpha ferrite, the matrix, and then you form iron 3C, which is cementite. This is a very unique iron-carbon phase diagram, and the alloying is very, very unique. Philosophically, can you tell me why it works? There are two major mechanisms of diffusion. Okay? There's a vacancy diffusion. What does that mean? I bring 1,000 people and I bring Backstreet Boys on stage right here. You know, every seat is going to be taken, unlike my lectures. You know? So how can you get a seat? And the diffusion happens like if humans come in, but let's say there's mice in this room or cats in this room. They can fit in between. So if I want to fill up this room with cats, so there's interstitial diffusion. And carbon atom is very small compared to iron. So it can go in between. Like I was driving today, there was a little bit of traffic, and there was a motorcycle. Any of you have a motorcycle? Nobody has a motorcycle? If there's traffic, it's nice to have a motorcycle. You know why? Because it can go between the cars. Right?
I won't say it's a good thing.
Okay. And the last one is martensite. Martensite, remember this word because martensite has BCT structure, body-centered tetragonal. And this is how it works. Tetragonal is because it's not cubic. You see, it's a little bit elongated in this direction. So that's why it's tetragonal, body-centered. This is the structure. It looks like needles. In austenite, there's like needles. And to achieve that, it is possible, but you have to drop down the temperature to like 200 degrees C. Very rapid. And by doing this, there is no diffusion involved. It's diffusion-less transformation. It only depends on the temperature. If you are capable to do that, typically for smaller parts. Large part, if it's hot, it's very hard to cool it down. But something that's small, you can imagine it's easier to cool it down fast, but huge. So from 727, whatever the temperature was, down to 200 and even less degrees. So if we do a slow cooling of the gamma FCC, we're going to end up with BCC alpha and iron 3C. Or we can quench it. The term is quench. Boom, drop the temperature down very fast. And then by tempering, we can go back to the structure. So martensite is a single phase. It has body-centered tetragonal structure, and it's diffusionless transformation. It happens when the carbon concentration is less than 0.15 weight percent. And as you can imagine, because it's kind of non-symmetric, it has less amount of the slip systems, slip planes. Okay, there are alloying elements that can be added to steel like chrome, nickel, moly, silicon, and manganese. And they retard this eutectoid transformation. The problem with all this stuff is that all of these ingredients are more expensive than iron. So that's why stainless steel is more expensive, because you're adding expensive elements to the steel. What is also useful is what's called continuous cooling. And continuous cooling is when you cool naturally, meaning that you're not sticking it into ice water or anything like that. It just cools by itself. And here's the cooling curve. The cooling curve you can measure. All you need is just a thermocouple. And then, if you have the nose curves and the cooling curves, you can figure out what microstructure you're going to end up with. An example, isothermal transformation diagram for 0.45% carbon. Sketch and label the time temperature path to produce the following microstructure. 42% pro-Ectoid ferrite and 58% coarse pearlite, 50% fine pearlite and 50% bainite, 100% martensite, 50 martensite and 50 austenite. And something tells me that for half of you, these words have no meaning. Is that right? Okay, well, that's where the phase diagram analysis comes from. 42% pro-Ectoid ferrite and 58 coarse pearlite. We have this nose diagrams. This is the time. And this is the percentage. Okay? I mean, is it worth for me to actually go through this? Yes? Okay. So if all austenite transformed to pro-Ectoid ferrite alpha and the coarse pearlite, the composition C0, whatever the composition is, minus 0.022, that comes from the phase diagram. Here. This is 0.022. So you need to have this diagram handy to do any kind of analysis. Divided by 0.76 minus 0.022. And we started with 0.45, that's what's given in the problem. And that gives you the fraction of pearlite of 58%. And the rest is going to be 42% for the alpha. And this needs to be done like just below the eutectoid temperature. So 727, you can see the temperature here. Here we have the transformation. And we can measure by how much. The second one was asking for 50 austenite, and so it's this dashed line. We drop it down to 590 and keep it for this amount of time, and that's how we're going to get 50% transformed. For the 100% martensite, which is here, we need to bypass the nose. And to do that, we need to quench it down to very fast to very low temperature. And that way, here's the 50%. So we drop it down right here to get 50% martensite and 50% austenite to 290 degrees. Remember, this martensite transformation is diffusionless. So this is kind of like really an exception from most of the rules in nature, because it involves local rearrangement of the atoms. They don't need to travel very large distances. It's like happening locally. How does this affect mechanical properties? Hypoeutectoid versus hyper. Here we have pearlite and ferrite. Ferrite by definition is soft. Ferrite is like pure iron, more or less. If we are above 0.76%, we have hypereutectoid. So we on the right side of that reaction. And we have cementite and pearlite. This is yield strength and hardness for hypoeutectoid steels versus hypereutectoid steels as a function of the composition of carbon. And it's counterintuitive if you look at it, because if you're on the left side, it's increasing. The properties are increasing with carbon concentration. If you are on the right side in the high per eutectoid, the properties are dropping with further increase in the carbon. You see? So you don't know. I mean, you need to know what kind of steel you have. So it means that you really need to know your initial composition. Does that make any sense? And who controls that initial composition? You. By either formulating your alloy, putting a certain amount of carbon, or purchasing it from the supplier. It's very unlikely that you're going to be working for a steel mill. I have been to a manufacturing facility that makes steel, which we'll discuss production at some point. It's very interesting. But most likely what you're going to do is you're going to go to Grainger catalog or whatever catalog and purchase a product from a company that supplies it. You can purchase different kinds of steels. You can purchase hypoeutectoid steel versus hypereutectoid steel. And then the heat treatment is going to be different depending on the composition of carbon. You see that here? Remember that gear that had this skin layer that was dark? That made it harder, remember? Do you remember? Anybody? Case hardening, yes. So you need to know what that gear is made from for this case hardening to work. Fine pearlite versus coarse pearlite and sphaeridite. Like sphaeridite, you're already like in pushing towards cast iron, which is more than 6% or whatever was carbon. Remember, martensite is the hardest ever structure there is. It's even harder than the fine pearlite. This is Brinell hardness for fine pearlite, for martensite, for hypo versus hyper. Now here you have a nonlinear increase for martensite and more or less linear increase for fine pearlite. And then there is tempered martensite, which is basically there's a lot of stress, internal stress that develops in the material, which needs to be released. So to release that stress, you need to do an anneal. Here's the plot that shows you the percent RA is the percent reduction of area. And there's always a trade-off between making the material soft versus making the material hard. And you can see it here. Increased percent of reduction of area is making the material harder or softer? All right, I'll ask you about the yield strength. Dropping down the yield strength, is the material harder or softer? Which material is harder? The one that is here or the one that is here? Yes, the one that has a higher yield strength is going to be harder. And this one is going to be softer. And for the reduction of area, you can see it's the opposite trend. So this is a very important graph that summarizes all of that we discussed today. We start with austenite, which is the gamma phase. And then we can slow cool, which is taking that sample and taking out of the furnace, and or maybe even cooling it with the furnace, just turn off the furnace. We have another one that we place in oil, and we have the third one that we place in ice water. We have 3 rounds. Boom, boom, boom. If we do it slow, we're going to have perlite. If we have moderate, we have bainite. And if we rapid quench, we're going to have martensite. And this is the strength versus ductility. Martensite, bainite, fine perlite, coarse perlite, spheroidite. These are general trends. This is a very important slide that basically like summarizes the whole like processing of steel. To control the process, to control the structure, to control the properties. Finally, I was able to explain to you how it works on a very important and one of the most important systems, which is steel, that's used everywhere. And the reason why is steel everywhere? Cheap, because it's cheap. And it has good properties. Okay, we talked about heat treatment and Avrami equation. Any questions? F of t is that transformation. Like how much of the phase was transformed? And this is the Arrhenius equation. And here's the extra D data. And the temperature versus integrated intensity of different reflections for titanium nitride. This is the parameter we're trying to calculate from the data. And you can see, look, we're looking at silicide formation. At 700 degrees C, only 16% transformed. This was for 30 minutes. At 750, it was 30% that was transformed. At 800, 31% transformed. We converted this into the thickness. 21 nanometers, 40 nanometers, 42 nanometers. And then made a Arrhenius plot. Well, Copilot made the figure. So I could explain to people what it's supposed to look like. You plot 1,000 degrees over temperature, and this is the log of the transformation rate. And you can calculate the activation energy based from that. And then, or it may look like this. It's all bogus stuff, but you know, if you've never seen something and you get a visualization, if it's more or less correct, and I know that it's correct because it's supposed to look like that. From this, we calculated or predicted the temperature versus time for 800 degrees, 700, 650. So it may look like this. We'll give you a processing window. Or the nose temperature versus 1 over T. Look, this is 10%, 30%, 90%, and here we will like identify where it is safe to do this processing. So if you want to do 1 hour, it's going to be at 627 degrees, 30 minutes, 644, 5 minutes, 685, or 1 minute at 715. These are predictions of how long it's going to take you to, finish this.
And hopefully we're going to be the first to apply this concept to ceramics, where right now it's like in a textbook for metals. This is going to be much more descriptive, chapter 11, dealing with classification and processing. You're going to have more of that if you take manufacturing processes, and also what heat treatment procedures you can use for both ferrous and non-ferrous alloys. You know, what's the difference between ferrous and non-ferrous alloys? Ferrous alloys contain ferrum, which is iron, and non-ferrous is the rest. So you can see steels and cast irons. So here are the steels, these are the cast irons. So let's focus first on the classification of the ferrous alloys. The steels can be low alloy or high alloy. And when you say low alloy and high alloy, that means in terms of what? Low what? And high what? Concentration of? Come on. It's right there on the slide. Steel is an alloy of iron and what's the second element? Carbon. Okay, so low carbon steel is below 0.25%. Medium is between 0.25 and 0.6, and high between 0.6 and 1.4. And then there's plain. An example is 1010. It cannot be hardened. It has low tensile strength and large elongation. That's what your car is made from. HSLA, you add chrome, vanadium, nickel, and moly. 4310, it can be hardened. Bridges, tower presses, vessels. Medium carbon, plain 1040 steel. Can be hardened, improved tensile strength, crankshafts, bolts, hammers, and blades. This is heat treatable if you add some alloying elements. 4340, two pluses here. Pistons, gears, wear applications. High carbon steel, plain 1095. It's good for wear. It doesn't wear very much. So you like. Then for tool, you add alloying elements. 4190. Drills, saws, dies. Stainless, chrome, nickel, moly. 304, 409. High temperature applications, turbine blades. Very corrosive, corrosion resistant. We're going to talk about corrosion. So here you're increasing strength, cost, and decreasing ductility. That describes all of the steels right here. How are they made? You start with the ore. Anybody have seen ore? Iron ore? It's red dirt or red rocks that comes from Australia. I've been to a production facility in China. They have stuff coming on the ships from Australia, this iron ore, and this refractory vessel is like higher than the ceiling, is big. So the heat is there, there's some fuel that's burned. So C plus oxygen gives you CO2. There's a reduction of ore to metal. So CO2 plus C gives you 2 CO. 3 CO plus iron, 2 or 3 iron ore is oxide, gives you iron plus 3 CO2. You can see that this production is kind of dangerous because there's CO that's produced and there's CO2 that's produced. So all of these people that worry about pollution and global warming and all that, this is producing a lot of CO2, this manufacturing. Then for purification, calcium CO3 gives you calcium oxide plus CO2. Calcium oxide plus silicon oxide plus alumina gives you slag. And this slag is here and you get molten iron. So you put iron, or you put coke, you put limestone into the blast furnace. You melt all this stuff and it's huge. Okay, let's talk about nomenclature. By AISI or SAE. 10 and then 2 X's is plain carbon steel. 11 is plain carbon steel that's resurfarized for machinability, that you can cut it. 15 means that there's manganese, 1 to 1.65%. 4 means there's moly. 43, nickel, chrome, and moly. 3 elements, that's why there's 3. 44 is moly, but larger amount, 0.5. This 2 axis is the amount of carbon times 100%. So that means that 1060 steel is plain carbon steel with 0.6 weight percent carbon. And if you talk about stainless steel, it's going to have more than 11% chrome. This is demystifying the nomenclature. Cast irons are ferrous alloys that have more than 2% carbon, typically 3 to 4.5. And they have low melting temperature if you look at the phase diagram, and they're easy to cast. And generally they're very brittle. So what you have there is you have cementite that gets decomposed to ferrite and graphite. And generally it's a slow process. You have not seen this, but this is the true equilibrium phase diagram. It shows you what happens at 90 and 100% carbon. Because here you're going to have liquid graphite, which is useless unless you're trying to make a part out of graphite. Another additive that gets there is silicon, because silicon is relatively inexpensive, more than 1 weight percent. There are 2 types: gray iron and ductile iron. Gray iron has graphite flakes. It's weak and brittle in tension, as you can imagine, because this sharp particles act as stress concentration points. But it's good for vibration and damping. And also good for wear resistance. There's also white iron and moldable iron. And here's the microstructure. And there's compacted graphite iron. All this black stuff is carbon. So you don't see this in steel because there's very little of it. And you put too much, then you have graphite, just like in your pencil. So here is the window for the production of cast irons. And you can have ferritic moldable versus ferritic moldable. Again, if you look at iron, cast iron, it's going to have graphite. It's pretty big, as you can see. In this case, there were cutting properties that were studied. And here's an example of the microstructure. This is perlite, this is graphite. 2 different cast irons were subjected to cutting. And then there was a drill bit Anybody of you ever tried to drill something? What do you want to have? Something like this or something like that when you drill? Yeah, why? Yeah, it doesn't get stuck, it doesn't fly, doesn't get into your eye. So this is better. Well, this is about a composite, so it's composite is different. What's important is oxidation, and we'll talk about like degradation again. You can see the difference in the microstructure of the two different materials. Oh, I made these graphs. Every time you see like good graphs, I made them. I'm sorry, like Kaleidagraph by default gives you like this blue frame. So you can see here, we're going to talk about oxidation as well, but this is 4 hours, this is 100 microns here. So 4 hours, it's about 50 microns, like size of your hair roughly. This is 24 hours, this is 48 hours, and this is 96 hours. And you get surface oxidation. Okay, problems with iron, it's heavy and it rusts. Those are the two major problems. Electrical conductivity, I mean, non-ferrous alloys are classified based on what kind of alloy it is. So we have copper alloys, we have aluminum alloys, titanium alloys, magnesium alloys, we have noble metals and refractory metals. Copper and zinc is brass, so if you do that, most of your fixtures, plumbing fixtures, are made from brass. Bronze there are more elements that added. They're used for landing gear, for example, because of the high crack resistance. Copper beryllium is used as improving the strength. Aluminum alloys are pretty big. This is aluminum right here. You see that that frame over that window is aluminum. It's as low density. It can solid solution or precipitation hard, meaning that after you're done processing it, if you just let it sit over time, it becomes hard. And aerospace industry uses a lot of aluminum. Magnesium alloy is even less dense. Also used for aircraft and missiles because of its low density. Sometimes used for laptop cases. Titanium alloys have half the density of steel. Expensive. a lot of space applications. The reason is it's hard to deform it because it has HCP structure, hexagonal close packed, so it has limited number of slip systems. Noble metals have very specific applications. Gold, platinum, silver. They're very corrosion resistant. And then you have refractory metals that have very high melting temperature, like moly, tungsten, tantalum. And next time we're going to talk about processing, how these things can be placed and formed into product. My undergrad major was in metals plastic deformation technology. Stamping, forging, extrusion, drawing, all that stuff. Because if you look around you, if you can find one part that's cast, I'll give you a prize. Do you have any questions? All right, so exam is going to be here on paper, and I want to give you a bonus problem so that you can raise the, yes?
Is this still going to be questions?
Yes, there's going to be problems. And I submitted the midterm grades. I didn't have all the grades because the TAs didn't give me all the grades, so they're not very accurate. I'm required to submit it, so I did it. You can see your midterm grades, but don't worry if they're like something that you don't like. It's okay. Stick around. Yes.
Is this exam going to be based on 5 through 8 or 5 through 9?
I haven't made up the test. That's my task for today and tomorrow, is to make up the test. Yes. I haven't made up the test. I will make it, and you know what I'm going to do? I'm going to bring the actual test in class. I'm going to say, this problem is dealing with this. Do you want that?
Yes.
What are you going to give me in return? All your love? Good teaching evaluations in the end? Yes? I want you to succeed. And, you know, I don't see students, I see students as my friends. Because I've been there where you are at, and it's not easy, I can tell you. And it's very stressful to take a test. You know? The TAs in another class, you know what they did? They put up the time. Tick, tick, tick. I said, why are you stressing them? Anyway, I see you Thursday.